I can feel the excitement in the air. Let's do this. All right, Elian, your hair is beautiful, but your eyes are better. Look here. So, does everyone have Unit 5 exponential function booklet? All right, excellent. Well done, Miss Sly, on causing some confusion this morning. Let's get started. So what I'm going to do today, so what we did is a little exercise where we experienced the power of an exponential function. When we just double a tiny number, it actually grows exponentially. Okay, if I were to triple it, it would grow exponentially even faster. So let's look at a graph of an exponential function. Okay, let's talk about the range and domain of that function. Let's talk about its asymptote and its y-intercept. And let's potentially look at the first and second difference of exponential functions. So nothing new today. Well, actually, not true. The only thing that is new today is a new function. Okay? All right. So first of all, on this graph, you have the graph of a function called f of x equals 2 to the power of x. So this function is doubling, right? Let's maybe write down next to it that it is a doubling function. I don't know how to write doubling. I think it's doubling, right? So it doubles everything. And then, yes, you said if I want to triple things, I would go 3 to the power of x. Okay, well, let's just see. So first of all, just notice, and I'm going to talk about this in a second. Notice what the graph looks like on the left side of the y-axis, right? It goes down, down, down. Okay, so what I want you to do right now is make an exponential function. Okay, mine is going to look opposite of yours because I'm making mine grow in the positive, right? So you're all looking like this, right? Because you're showing how the growth. Yeah, Gio, if you're in this class, you have to do it. I know, I'm sorry. That is the ticket. Astrid, Sonichka, where's your exponential function? Yes, Zach, we're waiting for you. All right. What if, no. What if I change it? So this is 2 to the power of x. What if I change it to 10 to the power of x? Nice. So we're saying it's growing exponentially, just faster. What if I change it to 0.5 to the power of x? I'm not going to give you the answer. Just curious. All right, let's see. So I'm not telling you, but your brain is already checked in. Okay, so what we know is, so if let's just do some work on the side. If we have f of x equals 10 to the power of x, let's just plot a few points, okay? So when I have x is 0, what is y going to be equal to? What is what is 10 to the power of 0? What is Miss Sly to the power of 0? Right? If x is 1, what is y going to be? 10, right? Because 10 to the power of 1. If x is 2, what is y? 10 to the power of 2. 10 to the power of 2 means 10 times 10. Good. If x is 3, guys, it's a new function. It's okay. We're making mistakes because we're just getting used to this. If x is 3, that means 10 to the power of 3. Okay, so we see it's growing and it's growing fast. All right, well, what happens when x is, you might need your calculator for this. Unless you're really good at square roots. What happens when x is 0.5? And why did I say square root?
Because it's
Yeah. 10 to the power of 0.5 is the same thing as 10 to the power of 1/2, which is the same thing as? Interesting. Okay, so when x is 0.5, give me one decimal place. 3.1. 3.2, don't forget to round. Thank you. Let's make x 0. Oh no, you know what we'll do? Let's make x negative. What if x is -1? So we're saying 10 to the power of -1. Do you need to pop that in your calculator? No. Ben, what do we do when we have a negative exponent? It's the reciprocal. It means it's 1/10, which is 0.1. Okay, what if my exponent is -2? Well, that's going to be 10 to the power of -2, which is 1/10 squared. What's that? It's going to be 1/100. Anyone know how to do that in decimals? 0.01. Take a guess what y is when x is -3. Take a guess. Look at the pattern. Yeah. 0.001. There you go. 0.001. It's one. Look, it's 1/10, 1/100th, 1/1000, 1/10,000. Okay. And we didn't look at this for the 2 to the power of x, but it's a very similar thing. It's just that 10 is easy to. So what I want us to do is plot these points. Let's plot the function of 10 to the power of x. Okay, so 0, 1. Okay, that's easy. Oh, look, 0, 1. It's the same y-intercept. That's interesting. When x is 1, y is going to be 10. Oops, I can't even do that. That's going to be somewhere all the way up there. Okay. Maybe I'll just say 10. Okay, when x is, what did we do? We said 1/2. Y is going to be 3.2. Okay. So about there. Okay, then we went into the negatives. At -1, y is going to be 0.1. At -2, y is 0.01. At -3, y is 0.00. How do I draw that, folks? What if, and here's the question, what if I have x being 1,000,000? Will y be greater than 0 or less than 0? Here's the question I want to ask. At what point can I make y -1? What is a value of x? 10 to the power of what will give you an answer of -1? Why not? That's right. I'm hearing the buzzword asymptote. We are approaching an asymptote. On your calculator, do 10 to the power of like 9999999, like the biggest number you can get. So maybe do a little smaller number. Did I not do attendance? Okay, do 10 to the power of, oh no, sorry. The smallest number you can get. Oh. The negative number. Hi, good morning. No worries. Yes. Yeah. Yeah. Sorry. I meant negative number, right? Because we want to find a way. So Try a really big negative number, like 10 to the power of negative a million. What do we get? Do I finally get my negative number?
0.
It's 0?
I got 0. I did 10 to the negative 9.
You got 0. Yeah. Something's wrong with your calculator. Yes. I'm taking out my calculator. Okay. So what you're saying is 10 to the power of negative. Oh, it's telling me it's undefined. It's too big. 10 to the power of, what if I just go negative 100? Okay. So it's telling me 1 to the power, 1 times 10 to the power of 100. What's happening is every time we increase the decimal in a negative way, we are dividing by 100. Or sorry, we're dividing by 10. Can I ever get to a value of 0?
No.
We cannot. And that's why, what are we approaching? The asymptote. We're getting closer. Each time our graph is getting closer and closer to 0. But we can never get a value of 0 when we have something to the power of an exponent. So if we take this 10 to the power of x function and we're trying to graph it, we need to keep in mind that that graph is approaching an exponent. And what we see, it's approaching an asymptote. And what we see is that 10 to the power of x approaches the asymptote faster than 2 to the power of x. Right? So let's trace our 10 to the power of x. And remember, it's when x is 1, y is 10. Right? So we can only sort of draw an arrow. And we're going to call this function f of x equals 10 to the power of x. And this blue one on my graph is called f of x equals 2 to the power of x. So what I'm seeing is, as the base of the exponent gets higher, it grows exponentially, but faster. All right. And then we had the question of, well, what happens when my function is f of x is 0.5 to the power of x? Right? So I'm saying, and then you were all like, so you were like this, you're like, oh, this is 2 to the power of x. This is 10 to the power of x. And then I said, well, what's 0.5 to the power of x? And you all kind of went, oh, it just goes really slowly. It's a slow exponential growth. Well, let's see. Now, 0.5 to the power of x, how else can I write it? Beautiful. I can write 1 over 2 to the power of x, right? Okay, what's the easiest point to graph here? When x is 0, what is y? 1. Why? Anything to the power of 0 is 1. So folks, what's happening to the y-intercept?
It's the same for all of them.
It's always the same. Interesting. All right. And now, if x is 1, what is y equal to? 0.5, right? Or 1/2. Let's do decimals because it's easier to graph. If x is 2, what is y equal to? It would be 1/2 to the power of 2. 1 over 4, which is the same as 0.25. So I'm going to actually write 1 over 4 so you can see. If x is 3, what is y? 1 over 8. If x is 4, what is y? 1 over 16. Now, in order to graph that, you need to convert it into a decimal. But can you see what is happening to our function? Is it exponentially growing?
It's shrinking.
It is shrinking. We actually call this decay. It is decaying exponentially. Well, I wonder what happens in the negatives. What if x is negative 1? Okay, what we're going to say is, oh, that means it's 1/2 to the power of negative 1. What does that negative tell me to do? This one. What's the word? What is it? It's 2 over 1. Beautiful. So remember, 1/2 to the power of negative 1 is the same thing as 2 over 1, right? The negative in the exponent indicates we're talking about a reciprocal. So when x is negative 1, y is 2. Oh, how about if x is negative 2? So then we're going to have 1/2 to the power of negative 2. What's that going to give you? Ah, that's 4. What if x is negative 3? Right, so I've got 1/2 to the power of negative 3, which is the same thing as 2 to the power of 3, which is 8. So is there some exponential growth? Yep, just backwards. What if I had x equals negative 4? What would y equal to? 16. Okay, so it's like it's doubling, but it's not doubling. What's the word we should use? It is halving. And doesn't that make sense? If our function is 0.5 to the power of x, this is a halving function. We are making up a word, but it makes sense to us, right? It is halving the value. So let's plot as many of these points as we can to see what this function actually looks like. Okay, so I've got the y-intercept. When x is 1, y is 0.5. Oh, when x is 2, y is 0.25. When x is 3, it's half of 25. Oh. So, right, we're seeing that as x gets bigger, y decreases. Will it ever reach 0? What's your hunch?
I don't think so.
Ah, interesting. Good math intuition. Yes. So again, regardless of whether the graph is growing or decaying, we have an asymptote at y equals 0. Okay, when x is negative 1, y is 2. When x is negative 2, y is 4. Whoa. So let's label this graph as f of x equals, and I'm just going to add a fraction so we can see 1/2 to the power of x. Now let's use the colors on my graph. My green graph is similar, let's call it symmetrical to which graph? Blue or orange? Oh, yeah. Do you see that it looks like what's a better word to use for what green and blue is of each other? What is it? Oh, someone said it. Ooh, it is a reflection. In which axis? In the y-axis. They are just reflections in the y-axis. Oh, so nothing new, Miss Sly, right? Just a little bit new, but we're talking about asymptotes. We're talking about reflections. We're seeing that 1/2 x is just a reflection of 2 to the power of x. Isn't that interesting? So the green one is showing exponential decay. Let's write that down. And the blue one and the orange one, they are showing exponential growth. And exponential growth and decay happen in nature a lot. And we're actually going to be doing some, even in mitosis, right? There is exponential growth. You have one cell. What does it do? Two cells, it doubles. You have two cells, what happens? Four cells. Four cells, eight cells. Folks, that's mitosis or meiosis, right? A natural thing. All right. Would there be an asymptote in the above graph? Why or why not? State the domain and range. Okay, so yes, there's an asymptote, right? We already mentioned that. So we're going to say asymptote at what? What is the equation of the asymptote? That's right. It's a horizontal asymptote. Oh, let's even say that. Horizontal asymptote at y equals to 0. And so far, we noticed that every single function that we drew has a horizontal asymptote of y equals 0. Okay, great. Then state the, and why is it? Why is it that there is an asymptote at y equals 0? Why will we never get into a negative? Yeah.
Because if you put something to the exponent and then 0,
There you go.
exponent 0.
That's right. With a positive, right? When our base is positive, no exponent will produce a negative value. What's the key word here? Right? Positive base. Notice all of our bases were positive, right? We'll play around with a negative base, but just note that as long as you have a positive base, you are always going to have a positive value. All right, let's talk about the domain and range. So for the domain, are there any restrictions in the domain? Will the graph ever stop growing on the x-axis? No, in theory, right? If it's exponential growth, it's going to take a really long time to get to x equals 1,000, but it will get there, right? So for the domain, we have no restrictions, meaning for all three functions, x belongs to all real numbers. Regardless of if it's decay or growth, it's the entire x-axis belongs to this function. How about the range? Yes, y is a set of real numbers, but there is a restriction. What is it?
Y cannot equal 0.
So can y equals -5? No. So give me more. Yeah.
As long as y is greater than 0.
Okay. Yeah?
Yeah.
Questions? How about, can it be y is greater than and equal to 0? Why not, Lila? That's right. Good. So it will never get, so notice, it's not greater than and equal to, right? We've been doing a lot of that in the other unit, not this unit. Okay, so literally greater than because there's an asymptote. Okay, interesting. All right, sketch the graphs of 1/2 x. Done. Done. Okay, we did that. Let's move on to the next page where we analyze our graphs. So there's a typo here. Make this 2 to the power of x. Sorry. This second one should be 2 to the power of x, not 10 to the power of x. Okay. So first of all, I want to show you another way of writing this first function of 1/2 x. What if I wrote it as 2 to the power of something? Anyone know how I could write it? Close, but no. Negative x, right? The negative implies reciprocal. Okay, interesting. All right. So what is the y-intercept of this one? 0, 1. Great. What's the y-intercept of 2 to the power of x? 0, 1. 10 to the power of x? 0, 1. We did not do 1/4 to the power of x, but what will the y-intercept be? You got it. What will the y-intercept of 1.3 to the power of x be? You got it. Do you think it's possible to have a different y-intercept? Come on, be creative. Think outside the box. How? Ah, thank you, Mustafa. What if we have a C value? Ooh. All right. Next, is the function increasing or decreasing? So do you see this? This means as x is approaching infinity. So as the x value gets bigger, meaning as we go from left to right, okay? Because we're always going from the left side to the right side. If you have your phone, put it away. Put it away. It's not worth it. Is the function increasing or decreasing? So when we have 1/2 x, was the function increasing as we went in this direction or decreasing? Good. Two to the power of x, increase or decrease? Increase. 10 to the power of x, increase. Take a guess. 0.25 to the power of x. That's a very good guess. Yes, it will decrease. Take a guess. If you have a graph, 1.3 to the power of x. I got to check this. I can't, right? How am I going to check it? Desmos. F of x equals, I'm just going to test 0.25 to the power of x. You got it. Look, this is 0.25 to the power of x. Let's try another one. F of x equals 1.3 to the power of x. Hey, good stuff. Yes, 1.3 to the power of x increases. Folks, how about 1? What if my base is 1? What will my graph look like? Interesting. Why, Lila? That's a really interesting math intuition. And it's interesting that you have that sense, but you're like, I can't even explain why. So, Luke, what do you think that? So this is the intuition that people are coming up with.
I think that no matter. Wait. If the x value stays the same, right? No.
So let's check first. Yeah, Greg? Like horizontal straight line. Oh, a diagonal straight line. Okay. Yeah. A vertical straight line. Folks, let's check it out. Let's check I love that we're using our math intuition. 1 to the power of x. Why is it a horizontal line? You got it. What is it? Greg, I cannot hear this beautiful thought coming to me. What is it? And you missed it. Bam, gorgeous. Okay. You might want to ask Lila to repeat what she said because it was some beautiful stuff. And folks, this is going to be if she agrees, I'm not going to let her repeat it again. So make sure. So Greg, ask her kindly, nicely. No. Yeah. No. Lila, yes. I was not paying attention. I'm so sorry.
I said 1 to the power of negative 10
Stays as was. At what? 1. What's 1 to the power of a million? What's 1 to the power of Miss Sly? 1. What's 1 to the power of negative 10? What's 1 to the power of 0? 1. So 1 is 1 to the power of x is the only function that does not grow exponentially. If the base is less than 1, we've got decay. If the base is greater than 1, we've got growth. Let's check. What if I do 0.99? Oh, interesting. Do you see? As I get, watch this. As I get closer to 1, it will flatten out. Okay, what if I get 1.1? Oh, do you see? And as I add decimals, it does more of growth. Interesting. All right. So a base of 1.3 is an increase. Great. Domain, folks. What is the domain of every single one of these functions? X belongs to all real numbers. And you know what we'll do? Have you ever seen these? Where you do quotations? It means it's the same for, yeah. Yeah.
With the 1 to the x function, would
Yeah.
that be, would the asymptote be on 1, or would it still be on the x?
There is no asymptote. It's just a linear function, actually.
Oh, I mean for the, what's it called? Like when it's like 1.1 or something, would it be?
Right. It's still an asymptote of 0. Y equals 0. Yeah, it's just getting there slower. Yeah. All right. So because the asymptote is at y equals 0, the range is always y is greater than 0. Right? So we can use quotations to say, hey, that happens each time. All right. So let's do our summary. We're not going to get to first and second differences. I don't want to rush that. All right. The graph of f of x equals b to the power of x is increasing. Now, b, we say, is called base, right? When you have an exponent, the number at the bottom is called the base. B to the x increases when b is what? Yeah. Beautiful. We wanted to say b is greater than 0, but no, it's b is. So when b is greater than 1, the function is increasing. And it's decreasing when what? And what? Yeah. Yeah. So this only works, this exponential growth only works when the base is positive. Blank is always an asymptote. What is the equation of our asymptote? Y equals to 0. Now, can that move, Mustafa? Really?
Yes, it's a vertical shield.
Oh, yeah.
If the y-intercept can move, the asymptote can move. But do we have, for this format, do we have a vertical shift? No, it's just b to the x, right? There's no c value. So tomorrow we might talk about some vertical shifts. The domain is always x belongs to all real numbers. And the range is always y belongs to all real numbers such that y is greater than 0. The y-intercept is always 0, 1. Yeah.
What's the range when it's f of x is y to the x? Is it still the same?
No, the range in that case is y equals 1. Because it's not, but 1 to the power of x is not in this unit, right? The only question you're going to get is why is 1 to the power of x not in this unit? So homework. I'm going to see. Okay, so for homework, you are going to complete NOP. but don't do this middle one. So for P, don't do the table of values because we haven't looked at the table of values. And also, you're not doing question 1 because, again, it's looking at the table of values. We're going to look at first and second differences tomorrow. Okay, so you're doing NOP and you're doing question 2. What type of function? You can do this homework in probably like 5 minutes. So if you want to do it now, you have 5 minutes.